Section 5.2, Mathematical Induction, Part 1, Proving Formulas. So this is going to be another proving technique for us, which is called induction, as opposed to the deductive method that we used in our previous chapter. So basically how induction is going to work is we're going to have some property, and we are going to start by showing it works for the very first option. We are then going to assume that it works for some random k option, and then show the following one, k plus 1, is also true. And here's some of the history behind it. You can think of this as the domino effect. We show the first domino falls, so if we then assume the k domino falls, but then prove that the k plus 1 domino falls, that is essentially what we are doing here. Alright, so as you're going to see, we're going to have that basis step, we'll have the inductive step, and then we are going to go from there. So let's see what that looks like. We're going to use induction to prove that 1 plus 2 plus all the way up to n is n times n plus 1 all over 2 for every integer n greater than or equal to 1. Generally, these problems have a clear starting point. So we want to do that basis step first, once we've identified, of course, our property. Here is our property. So our basis step, we're told that n has to be greater than or equal to 1. So we start with 1. Does it actually work at 1? And if we compute both sides, we do get 1 on both sides, so it does work. So we then have our inductive step where we make an assumption. So we're going to say k is an integer with k greater than or equal to 1, the same properties as n, and we're going to take that property and put the k in there, and we're going to tell people that we are assuming this is a true statement. Well, what does p of k plus 1 look like? This is what we're hoping to get to, and I often start by writing it out just to clearly see what it is I'm trying to prove, and I will do some simplification here. So for example, k plus 1 plus 1, let's just write as k plus 2, because that's so much easier to see. So again, I'm going to clearly write out this is what I then want to show, so that I know what I need to prove. And then the question is, well, how do I get from the one to the other? A very common step that we will see in induction is that we will change the one to get to the other. So I'm going to add k plus 1 to both sides of the equation. I get the left-hand side of the p of k plus 1 pretty easily, and then let's look at that right-hand side. How does that one work? I get a common denominator. I'm going to multiply out those numerators, and then add up to get k squared plus 3k plus 2. And at that point, I'm hoping I can factor it. And yes, I can. It does factor as k plus 1 plus k plus, or times k plus 2, which, if you remember, this is what I was trying to get to. So here's my full proof here together. So again, you can see that basis step. Our inductive step, again, I am clearly making this assumption. Here's what I want to show. I've got the left-hand side and the right-hand side. You'll notice this assumption step I often label as equation 1, just so you can see what I am doing. So I added k plus 1 to both sides of it. So I have the left-hand side of what I wanted, and then just as before, I do the same work to the right-hand side, and I compare that to what I wanted. It is the same, and I make that statement, which is what we wanted to show. And so there is how I do an inductive proof. Very similar to your textbook author. I'm just presenting it a little bit differently. And so we have now proven that, and we can now say that that is true. Well, let's try applying that formula to a couple examples. So let's say we've got 2 plus 4 plus 6 all the way up to 500. You'll notice we do just have the evens there. So I'm going to write that as 2, and then times 1 plus 2 plus 3 all the way up to 250. So let's do the formula up to 250. So there's my formula. And then we crunch those numbers, and of course multiply the 2 out in front, which gets me 63,750. Let's say we want to add from 5 all the way up to 50. Well, this is the same as adding from all the way from 1 to 50, except I'm taking off 1, 2, 3, and 4. So we'll do the formula all the way up to 50, and the sum of those is 10. So I'll just subtract that 10 off the end, and I get 1,265. Last but not least, if I want to go to some arbitrary number, h minus 1, again, I plug that into my formula, and then simplify as much as I can. One very common sequence is called the geometric sequence, and here one of them is 1, r, r squared, r cubed, up to rn, and so on. We can also take a sum of that, and once we run that out and simplify, I will get r to the n plus 1 power minus 1 all over r minus 1. And that is the sum of a geometric sequence. So let's go ahead and actually prove that. Do note we are skipping 1 there. So again, I'm going to kind of skim past what your textbook author does, but there is talking through step by step where all of that comes from. And I'm going to hop up to my full proof here so you can see it. Here's my basis step. I can see that I get a 1 on both sides. My assumption step, again, I'm assuming this is true, so that I want to show that k plus 1 term. Again, I'm going to write it out and then simplify just a little bit so I can see it more easily. Much like my last proof, I'm going to add that r to the k plus 1 to both sides of equation 1. So I get my left-hand side right away. So now it's really just this right-hand side that I need to mess around with. I start by getting a common denominator of r minus 1. And here I am going to distribute. So that gets me r to the k plus 2 minus r to the k plus 1. And the r to the k plus 1s are going to cancel. So I will get r to the k plus 2 minus 1 all over r minus 1. And that is exactly what we wanted to show. And now that we have that formula, we may use it whenever we wish. And that is section 5.2.